Hello, I welcome you again to this all-important class where we will continue with our discussion on Laplace transform. Yes, you will recall in our previous class or in the video before this, you were introduced to Laplace transform, the definition of Laplace transform, some properties of Laplace transform, and we solved simple problems involving Laplace transform, where we looked at uh, the Laplace transform of a unit step function, the Laplace transform of an impulse function. I also looked at the Laplace transform of a sine function. In this class, we'll be moving our studies further to the inverse of Laplace transform. You know, in the previous class, like we said, we saw by definition that the Laplace transform is the transformation of signal from the time domain to the frequency domain. Of course, in this class, we'll be looking at the reverse, how to move a function from the frequency domain back to the time domain. We know one of the advantages that we enjoy with the Laplace transform is its ability to provide a very complex mathematical problem in time domain to the frequency domain, where we could simply solve that problem easily. Then finally also convert that problem back to time domain, and that provides us with its actual solution in time domain. So here we're going to be looking at the inverse Laplace transform. And if you have watched the first video, then you'll be ready for the second one. Now let's move into the class. The inverse Laplace transform. Now you can see that here is a symbol for inverse. This -1 here, this is the Laplace. This -1 here represents what? Inverse. And the inverse from frequency domain back to what? Time domain. Now we have two cases where we are expected to carry out the inverse Laplace transform. Case one is when we have a frequency function, say n of x. We can obtain its inverse f of t as what? N of t. But how do we achieve this? By matching the entries in the Laplace pair table. I'm going to show you the Laplace pair table here. Some of the functions in Laplace transform have been calculated in the frequency domain. And from that table, we can easily look at it and find out what its equivalent is in the time domain. Then we have case two. If you have a function of this form as a polynomial, if you have a function in this form as a partial fraction, so this f of t can be obtained by what? First step, decompose the function f of s into simple terms using the partial fraction word expansion. Then step two, find the inverse of each term by matching the entries in Laplace pair table. What do we mean by this? As we move deeply into this class, we'll get to understand what we mean here. So let's go in. Now, this is the Laplace pair table. So here you can see when we did the impulse function, Dirac of t or d of t, that's that. We said in frequency domain, remember that we said it is 1 everywhere, so we got 1. U of t, the unit step function, remember that we got 1 over x. I hope you have not forgotten in our last class, the ramp function t. Remember, one of the assignments I gave to you is to calculate t u of t, find the Laplace transform. Yes, when you do that, you should have 1 over s squared. When you have the exponential function, exponent of minus a of t will give you 1 over x plus a. What if it is exponential e of t? Then now you should know what this should look like. Then the sine function, when you have the sine function, it will be omega squared all over that, sine squared plus omega squared. When you have the cosine function, you're going to have that. We have the damped, a damped function. You are going to have that damped ramp function. When you have the damped sine function, you're going to have this. When you have the damped cosine function, you are going to have this. Now, remember what we said, when you have the exponent multiplying this, is going to cause what we call frequency shift. And you can see, rather than us having for sine, where you should have omega all over that, because of this shift here, it is creating a shift in the frequency of what? A. This side creating a shift also of what? Of A. So while you have this in your mind, this is the Laplace pair table. And this table will be consulting seriously for the inverse Laplace transform. That is to say, when we have, at the end of the day, if our frequency term is 1, its inverse will be what? Dirac of t. If our frequency term is 1 over s, its inverse will be u of t. If our frequency term is 1 over s squared, its conversion in time domain will be t. If our frequency term is 1 over s plus a, its function in time will be exponential a of t. So when you see 1 over s plus a, you should be seeing exponential a of t. When you see this, you should be seeing sine omega t and the rest of that. So let's continue. Now let's look at an example. We say find the inverse Laplace transform of this function. Now you can see this is f of x is equal to 3 over x, 5 all over x plus 1 plus 6 all over what? X squared plus 4. Now, how can we deal with this function? How do we deal with it? Solution, we have f of t. We're going to look for the inverse Laplace transform of each of these. Each of these, the inverse Laplace transform of this, inverse Laplace transform of this, inverse Laplace transform of this. And how do we deal with that? Now, simple. When we say f of t will be equal to, now this is 3 over x. Let's look at our table and see what 3 over s will look like. 3 over s is looking like this. You can see that this can be gotten 3 over s. This can be, in place of our own, this will be 3 times bracket 1 over x. So which is what? U of t. So we can say that 3 u of t, this u of t here is multiplying that. So we can say 3u of t. So you can see that. Now this is minus 5 exponential minus t. Look at that. So minus 5 exponential. This is, we can bring out this 5. And we're going to have 1 over s plus 1. So 1 all over s plus 1, what is it going to give to us? Let's look at our table. 1 over x plus 1. So 1 over x plus 1. Here we have x plus a. So it then means a here for us with the word of the 1, which means to say we're going to have exponential minus t. But because we have 5 in our own case, ours will be 5 times into 1 over that. So you can see that. So we can bring out 5 here so that we're going to have 1 over x plus 1. And so we can say 5 exponential minus t. In this case, you can see here, this is 6 all over s squared plus 4. So we can afford to, so that we can make this appear to be 2, we can reduce this to 3 times 2. So you can see the analysis here, 3 times 2 all over s squared plus 4. So 3 times 2, s squared plus 4. So if we want to do that, simply we can bring out 3 outside here. So we just have 2 all over s squared plus 4. Let's look at which one looks like it. 2 all over s squared plus 4. So you can see, so this is the one that looks like that, where our omega here will be 4. So you can see 2 squared here will be 4, whereas here will be 2. So s squared. So let's look at it. So you can see that's what we have here. So we can say 3 times what? 2 all over what? s squared plus what? 4. So we can bring out 3. So the function that accommodates that is sine 2t. And we'll have that. And you can see we've been able to resolve this into what? The time domain. Mind you that we are considering this from the one-sided Laplace transform perspective, and that's why you are seeing we're saying t for t is greater than or equal to 0. That is, we're considering only the Laplace transform from t starting from 0 down to what? To infinity. That's why we're saying greater or equal to 0. And mind you, we are also introducing u of t to help us understand that we are considering a function that is moving from what? From 0 to what? Minus infinity. So this is an assignment for you. Why don't you try this and see what you are going to get? So give this a try and let's see what you are going to arrive at the end of the day. Okay. So thank you again. So let's move to our next class. Now let's consider another example. Now we have that find f of t, given that f of x is equal to x squared plus 12 all over what? X into x plus 2, x plus 3. So you can see in this term, this is a reflection of this. Remember, we tried to show you that there are two cases when we are doing, we are going to be looking for the inverse Laplace transform. The case one is when you have ns, and another case two is when you have ns all over d of x. Now, what we mean here is you have the numerator is a frequency function, the denominator is a frequency function. You can see that, but the case we considered before now, we just have only one frequency function. But in this case, you have both numerator and denominator. They are all functions of what? S. When you have this, we said you can no longer go through the direct method. You have to go through the what? The partial fraction decomposition. So we have that step one. What do you do? Step one, you decompose f of s into simple terms using partial fraction expansion. So when you decompose it, you're going to be having this into, now you can see that the denominators, a all over x plus b all over x plus 2 plus c all over what? X plus 3. So this is how you break down this. So what we're going to be looking for now is the constant a, b, and c. We're going to be looking for the constants a, b, and c. So how do we look for that? So we're going to be looking for it using either the residue or what we call the cover-up method to determine a, b, and c. That is this constant. So let's look at the cover-up method. It is important for us to realize that there are several methods to do this, and I believe you have done partial fraction in the lower classes where you were shown how to find out these constants in B and C. Here, we're just going to be doing a little refresher of this so that we can find them. We have two methods, the algebraic method and the cover-up methods. There are other methods depending on whichever one you find convenient, but for now we're going to consider the cover-up method. So let's look at it. Now, if we apply the cover-up method, we're going to be looking for A will be equivalent to what? S of x. Yes, then we consider when x is 0. Now, it's important you see how this method is applied. So in this case, we look for how to eliminate x. One way to eliminate s is to make s what? x0. So when we make x0, what we do, we just look for a, when we make x0, look at it here. So that's what we're doing. We make x0. So we multiply that x also by f of x. When we do that, you see, we're going to be multiplying this whole function by x, right? Multiply this whole function by x, that is all through by x, make s of 0. We are covering this side. We are covering this side. We're just considering this side. So multiply this side by x. You get that? Then substitute for x is equal to what? 0. Now let's look at it. So you can see, so we're multiplying f of x by x, which is this function by x. So you can see, normally we're supposed to have x here. So when you multiply this by x, that x cancels. Then we'll substitute for x is equal to 0. Now when we substitute that, you can see you have 0 squared plus 12 all over what? This side would be the numerator. The denominator will give you this is 0 plus that. You're going to have 2. 0 plus that, you have 3. So at the end of the day, this is going to be 2. So we do the same thing also to find b. To find b, we cover up this side, we cover up this side, and we multiply this whole expression by what? By b. Mind you, this whole expression is actually f of x. So when you see us multiplying by f of x, you understand what we mean. So multiply this times what? This whole function, which is f of x. When you multiply that, you see this will cancel this. Then we substitute for x is equal to minus 2. Minus 2. Now look at it. So you see, we do that, then we substitute for x is minus 2. So you see the function now. So you can see that s, when you multiply that, what you're going to be having now is this. So you can see that. So we don't have s plus 2 here is gone. So you substitute for x is minus 2. So when you substitute for s is minus 2, you're going to have this, which is yes, minus 2 all squared plus 12. Yes, this is minus 2 times what? Of course, this is minus 2 plus 3. You know it's going to give you 1. So at the end of the day, you're going to have minus 8. So we do the same also for this. So we cover up this 2, then multiply this expression by x plus 3. When we do that, we're going to have x squared plus 12 all over what? X into x plus 2. Then we substitute for x is minus 3. Now let's see that. That's what we're doing. We substitute for x is minus 3. So when you substitute for x is minus 3, so at the end of the day, you're going to have this. So by the end of the day, we have gotten our A, B, and C. Why our A is 2, B is minus 8, C is 7. Then we substitute it into our equation. We substitute that into this. So you're going to have, this is A all over that. So having done this, then we'll move to the next step, which is find the inverse of each term by matching entries in the Laplace transform table. Of course, you know this in the Laplace transform table is equivalent to 2 times 1 over x. 2 times 1 over x, just like you have here, 2 times 1 over x. So what is 2 times 1 over x? So now we know that 1 over x is equal to what? 2. Is equal to 1 u of t, which is equivalent to, when you multiply by 2, it becomes 2u of t. So this is 2u of t. In this case, you have 8 all over this, which is equivalent to, say, 8 into 8. You can bring out 8 into 1 all over s plus 2. So 1 all over s plus 2 is the same thing as exponential minus 2t. Exponential minus 2t. Now, because of this constant 8, we multiply it by the 8. So in this case, this is also equivalent to, say, 7 into, you can say 7 into 1 all over what? X plus 3. Of course, so 1 all over s plus 3 from our table, of course, you know what is going to be 1 over x plus 3 is equivalent to what? exponential minus what you should have here, 3t, because we are a now here for us is 3. So you're going to have exponential minus 3t. Now, because we have our 7, it is going to be 7 exponential minus 3t. Now, mind you, we are assuming that all these functions, we are dealing with what? One-sided Laplace transform, that we are considering functions that are moving from 0 towards infinity, but not less than 0. So now you can see that. Yes, so you can see that. So that's the solution now to the inverse Laplace transform of this particular function that has been given to us. So we've been able to find its inverse Laplace transform. So I hope you got that clear. So if you don't get that, just following the same procedure, try out this. Yes, of course, when you try out this, you're going to see it's very simple. It's going to take you down to a very reasonable solution. And I don't think you're going to have any challenge if you follow the steps the way you were shown. You are certain to come out with the solution accurately without making any form of error. Anyway, I hope it is simple enough. Now, when you solve this expression, what you should be getting is exponential minus t. Okay, let me just put down the solution there, so that you can appreciate what you are doing when you finish solving. That will be very fine. Yes, so you can appreciate what you're doing when you are through. Then your solution will be you're gonna have at the end of the day exponential look at that. Okay. Okay, we're gonna have this exponential minus t. Okay. Exponential minus t, then plus, okay, 3 exponential minus 3t, 3 exponential minus 3t. Okay. Okay. Yeah, 3 exponential minus 3t, then 4 exponential minus 4t. Yeah, then that, we're gonna have 4 exponential. Okay. Okay. Exponential minus 40. Then u of t. Okay. U of t. Okay. This should be minus so that we don't make mistakes. Okay. Then of course you know very well we are considering the function for t, of course, greater than or equal to 0. Okay, good. So this is what you're going to have as your answer when you try to solve that problem yourself. And I encourage you to try it so that you can appreciate what you've learned. Is an advantage. Okay, So let's move to the next one. So let's look at another example here. We have this function given that v of x, a function in frequency domain, is equal to this. Remember that this is also of the form ns all over what? D of x, that is the numerator and the denominator, they are all a function of what? Frequency. So we are asked to find v of t. That is, you are to find the inverse Laplace transform. So because we are to find it in time domain, this is frequency domain. So you are asked to find it in time domain, which is of course the inverse Laplace transform. So if we still go by the same method that we've been doing, knowing that this is of the form ns all over d of x, we are going to solve it in steps. First and foremost, by decomposing this into words, partial fractions. So when we decompose that now, you can see this here is going to be a all over x, one of that, b all over x plus 1, c all over this. Now, because this is a repeated root, we're going to have c all over s plus 2 squared, and also d all over what? S plus 2. Now, this is a repeated root kind of problem. So please, it's important you understand the difference between what we are doing now and the previous one. So now you can see that then we are to determine A, B, C, and D. So we're going to use another method called the algebraic method. We're going to use the algebraic method. Now, it does not mean that the cover-up method cannot work here. Maybe I'll encourage you to go and try it and see how far you can solve it using the cover-up method, of course. And I think you're going to enjoy that if you try with the cover-up method. So give that a try. But then it is somehow a little complex when you go with the cover-up method. With the cover-up method, you can find this, you can find this, you can as well find that. But I think this is going to be some kind of challenge with the cover-up method. So here we're just going to apply the algebraic method so that we can determine the constants. Now, to determine the constants ABC, we use the algebraic method. Now, cross multiplying, what do? We cross multiply, just like you have this. This will cross over this, all right? This will go towards this side. And when you cross multiply, mind you that all of this is what you have here. When you cross this, this will cross here. So of course, when you cross this, now you're going to have, at the end of the day, this will cancel all of that. You're going to have then that. So you're going to have this crossing over here. Now, when this crosses over here, now multiplying A, you know definitely well that now you can see it here. Look at that here, all of them multiplying. So when you have this multiplying A, you have X, so cancel this X. So you're going to have A into these two components, that is this and this. Then in this case, B, you're going to see B would cancel this. So you're going to have this multiplying B. So when you come to C, you have that this squared will take away this. So you're going to have this multiplying C, which is this. Then when it comes to D, of course, you're going to have just one of these going. So at the end of the day, one of it. So at the end of the day, you're going to have D multiplying X, this, and one of this, which is what we have here. Wow, so good. Having established this, the remaining is your power to expand. You begin to expand. So when you begin to expand, you know definitely this is going to be X, you know, of course, you should expect that what you should have here should be X plus 2 and another X plus 2 because they are 2, of course. And when you have that, you expect that they are going to expand themselves. And when they expand, you're going to be having something like x squared plus 4x plus 4. I don't know if it makes sense to you. You're going to have x squared plus 4x plus 4. I believe so. Then you now remember, then you now begin to multiply again that which you have, you multiply again by what? X plus 1. When you expand everything, you should be having a into s cubed plus 5x plus 8s plus what? Plus 4. Then in this case, you're going to be having, remember here, you are having, in this case, when you expand, remember we said you're going to have s squared for this side, s squared plus 4x plus 4. Now that is also going to be multiplying x. So you're going to be having s cubed plus 4s squared plus 4x because of the last 4. And in this case, you're going to have this s multiplying this, which is s squared. Now this s multiplying 1, which is going to be x. Of course, when you come here, you're going to have this multiplying this s squared, multiplying the other one, you're going to have x. So you're not going to have at the end of the s squared now times this, which will give you s cubed, s squared times that, which is going to give you 2x, of course. Going to give you 2x. Then you're going to have of course, you're going to have, remember we have another x here, so you have this, we multiply, this, of course, you know, this is already x, this is s times this will give you s squared, so plus the former 2s squared, you're going to have 3s squared, and in this case, you're going to have this x multiplying these two, you're going to have 2x. So expand this, you see, when you expand all of this, you're going to have this. So when you do that, I want you to pay attention to this algebraic method. So we now take out the coefficients. So what we do is to remove the coefficients. So now when we look at this point we have the first coefficient, we have 4, which is a constant. So all the constant terms here, we're going to take them out. Good. Oh, we are having this repeating itself. Okay, let us just take it out here so that will not be confused. Okay. Okay, so let's look at that. We're having this man double here. Okay, so that we can, okay, so that we can have a simple problem to deal with. Okay, that's fine. Okay, so you can see that. So we bring out the coefficient. So first and foremost, we start with the constant. So this is the constant, which is 4. So I have 4 is equal to, so we look at the one that is constant. So you see another constant here is 4a. Every other one has s, every other one has s. So the only one free here is 4 is equal to 4a, which is a 4 by this side is equal to 4a. And thereby we say, if we make a the subject, a will be equal to 4 over 4, which is the same thing as what? 1. And we call that equation 1. And then we look at another coefficient, which is x. We can see here on this side, x as a coefficient. If we look at here, s as a coefficient, we see there is none that is simply s here. So we just say it is 0. But on this side, we take out all the functions of x. So which ones are the functions of x? So when we look at this place, we see a 8s. Can you see that? So we are going to see 8s. So we can see, so we can just say 8a, which is a function of x. Then this side, which is also a function of x, we can see 4b. So this side, which is a function of s, we can say also what? C, only C. So this side, which is a function of s, they will have 2, then 2b. So you can see that's how we establish this. So let's look at the next one, the function of x squared. Of course, when we get to this side of the equation, we have x squared. So the coefficient here is 10. So we can see, we can take 10 here, then we look on this side of the equation, all the coefficients of x squared. So x squared, do we have x squared? Yes, we have a 5, we have 5a, we have 5a, which is this. Then this side we have 4b, which is this. Then this side we have, yes, c, of course, which is this. Then here we have 3d, because this is a coefficient of s squared, so 3d. So you can see we have that here. So the next one is s cubed. Now you can see here the coefficient of s cubed here is 0, which is, it doesn't exist. So we say its coefficient is 0, is equal to, so which ones with s3? We have a here, which is simply a. So we have this side, the coefficient is b. What about this side? We know s cubed. What about this side? We have 1, which is what? D. The coefficient is d. So we say a plus b plus d. You understand? That's what we have here. So simply we can substitute for a is equal to 1 here, because we already know that a is equal to 1. When we do that, we see we can now have, yes, 0 is equal to 1, which is a, plus what? B plus what? D. So we can simply say B plus D is equal to what? Minus 1. We can call that equation 4. Is that clear? Okay. In this case, you can see what we just did here was to also substitute A is equal to 1. So that we have 8 plus 4B plus C plus 2D. Yes. So therefore, we can say 4b plus c plus 2d is equal to minus 8, because this 8 will cross the equality sign. In this case, we see we can also do the same thing. And we have that 10 is equal to what? 1 plus what? 4b. Can you see that? Okay, now look at this. When we substitute a is equals to, here we have that a is this. So this should actually be 5. So let's correct that, so that we don't make mistake. Okay. Yes. 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 Okay. So let's make progress. Good. So we can say, yeah, when we substitute a is equal to 1 here, so this brings us to 5. So we can see 10, which is just 10 here. 10 is equal to 5 plus that plus that. So we can see 4b plus c plus 3d is equal to what? 10 minus 5, which is equal to what? 5. For that equation 3. So now from those equations, we want to find d. So our d, how do we find d? We can find it by saying equation 3 minus equation 2. This is equation 3, this is equation 2. If you subtract, you're going to have 5 minus 8. That should give you 13. You're going to have 3d minus 2d. You are going to have d. You are going to see c minus c will be 0. 4b minus 4b would also be 0. So the only function we'll be left with is d is equal to what? 13. So, and that's what you have there. You see 3d minus that. So you are going to be left with d is equal to 13. So we also know that from equation 4, from our equation 4, which is this, that we have b plus d is equal to what? Minus 1. So if that is correct, so we can say b, can we say b finally, make b the subject here, can say b is equal to minus 1 minus d. Can see that? Minus 1 minus d. So we know that our d is 13, so minus 1 minus 13 will give you minus 14. So we have our d. So with that, we can now using equation 2, that's our equation 2, we'll be able to look for what? What again have we not found? We have not found our c. So we'll be able to say C from here. Or from here, we can say our C is equal to -8 minus 4B minus 2D. Yes. If, for instance, we decide to use our equation 2, so we can see, or we use you can use equation 2, you can use equation 3. Let's assume we used our equation 3 because what we use here is equation 3. Let us correct that so that we are all on the same page. Okay, so yeah, so we'll be on the same page. Okay, sorry about the distraction. Okay, so when we do that, so now let's look at that. So when we use our equation 3, yes, we'll be able to say that C will be equal to what? 5 minus 4B minus 3D. Already we know what our B is, we know what our D is. On substitute, we're going to be having 22. So we've been able to find our constants. Yes, using the algebraic method. Good. This is one simple method that is generally applicable, and it is generally the widely used method. Yeah, but the cover-up rule is shorter and quicker and faster. Yes, but it has its own shortcomings. So we have that, hence we'll substitute our constants now when we substitute them. So you can see, having substituted them, this is what we should have. So of course, you know definitely well from our Laplace transform table that 1 over x, the Laplace transform is actually what? 1 or u of t, 1, or either you can say u of t. You can say 1, we can say simply u of t. Mind you that this u of t is multiplying everything in this bracket. It's common to all of them. So we can say 1. So this will become 14, then exponential minus t. Of course, remember in the first case, what we'll say, this will be 14 times 1 all over x plus 1. Good. 1 over x plus 1 in time domain is exponential minus t. So with the 14, then it's 14 times exponential minus t. In this case, you also have, this should be 22 times, okay? 22 times. In this case, 22 times 1 over x plus 2 squared. So mind you that this is a time shift. If you go to your Laplace transform pairs and look at our table, you will get to see that this is a time shifted function. You can say I'm a frequency shifted function, that the frequency has been shifted by 2, meaning that there is a multiplication of x raised to the power minus what? 2t. So that is what created the shift. So it has shifted this function, and that's why you have the minus 2t there. And then this is a ramp function, which is equivalent to saying t, or 1 over x, you remember 1 over x squared. So, but now that s, which is the frequency, has been shifted by what? By plus 2, and that's why you have exponential minus 2t. So, wow, this is where we've come down with this, and this is a solution. So now, I believe so far we've been trying out some of these things. You should be able to try yourself on this. Now, try this. G of t if g of x is this. So here we have to find g of t if g of x is this. Given that g of x is this, determine g of t. So we can see the answer here. So give it a try and see what you come out with at the end of the day. Okay, then the next thing we may be considering also in this class, but we wouldn't go so much into it, is the convolution integral. Yes, one beautiful application also of the Laplace transform is its ability to resolve convolution integrals for us. Now, what is convolution? Convolution, like we know, is the combination or the folding of two signals, and at the end of the day, we are achieving a new signal. So we can have two signals come together, folded together. At the end of the day, it will produce a new signal. You look at where do we really see the application of convolution? Let's take, for instance, you have a filter. Most times this AI, now you just bring a picture, you run it, and before you know it, you beautify the picture comes out spotless and beautiful. What you have really done is to run in two signals against themselves, the filter signal and the main signal. So the main signal passes through the filter, and the filter works on it, and you produce a new signal at the end of the day. So that process in mathematics is what we term as what? Convolution. So if we have if we have two signals, you can see that the convolution of two signals consists of time reversing one of the signals, shifting and multiplying it point by point with the second signal, and integrating the product. Now, this is how convolution is achieved mathematically. So you can see y of t is equal to what? Now, this is the first signal. Now, this is the second signal. It has been time shifted. It has been delayed by what? Tau. So you begin to integrate step by step until you achieve what? A new signal. So mathematically, it is written in this way. So you always see convolution. This is like a star, S of t times h of t. You understand? Then it gives you a new signal, y of t. So, but using Laplace transform, instead of trying to evaluate this using this integral, we can afford to deal with it in this form. Y of x is equal to s of x times h of x. So you simply look for the Laplace transform of this signal, look for the Laplace transform of this signal, find it in frequency domain, then multiply it together. You're going to have a new signal y of x. So at the end of the day, it will be easier for us to multiply these two signals. By the time we are done with the multiplication, we'll come back and do the inverse Laplace transform so that we can achieve what? Y of t. Instead of going through this process of point by point integration so that we can find the convolution of the signal. So you can see that Laplace transform is just a very interesting tool. It makes our mathematical analysis in most cases very, very easy. Okay, so that's that with convolution. Thank you very much for listening to us in this all-important class. Yes, we're going to take you now finally on the last class where we're going to be looking at the application of Laplace transform. I hope this class has been an interesting one. Please ensure you carry out all the tasks that you have been given. Good, you have the answers to help you as a guide. So when you don't get the solution, you can try again, or perhaps call our attention where you will need our help. So thank you so very much. If you enjoyed the video, I wait for you to watch the third one where you're going to appreciate again the Laplace transform. So thank you so much for listening, and do see you. Want to see you in the next class. Thank you, and bye for now.